The objective of this lecture is to describe kinematics of a rigid body. Now, a rigid body is defined as follows. A rigid body denoted R is a collection of at least 3 non-collinear points that may or may not contain mass. Such that the distance between any 2 points in the collection is constant. Now, when you look at the definition of a rigid body, it looks a lot like the definition of a reference frame. And that's because a rigid body kinematically is the same thing as a reference frame. So kinematically, a rigid body is a reference frame. The difference between a rigid body and a reference frame is that because the points of a rigid body may contain mass, when it comes to kinetics, when it comes to the motion of a rigid body due to actions applied to the rigid body, there's a distinction between a rigid body and a reference frame. A reference frame is more of an abstract notion of an object that doesn't have any mass, which is used to describe or observe motion, whereas a rigid body is an object that actually has mass. But from a standpoint of kinematics, a rigid body and a reference frame are exactly the same thing. Now, the key thing that we are interested in with rigid bodies is we're interested in how points move relative to one another in a rigid body. So the first thing that we are going to do is we're going to describe the velocity and acceleration between points on a rigid body. Now this description of velocity and acceleration between points on a rigid body is done as follows. As we'll say, let R be a rigid body. And then furthermore, let Q and P be points that are fixed in R. And finally, let A be an arbitrary reference frame. Now, the way a rigid body works is as follows, is that, and the velocity and acceleration between 2 points on a rigid body works as follows, is that here's my arbitrary reference frame. I'm going to call it A. And here is my rigid body. I'm going to denote it R. And I have 2 points. Let's suppose first that I define a point O, where O is fixed in A. O is fixed in A. And then I have 2 points which I'll define as Q and P. Here's Q and here's P. And the position of P relative to Q is going to be this vector which takes me from Q to P. So this is the position of P relative to Q. Now, here's where we start. Because Q and P are fixed in R, that implies that the position of P relative to Q is fixed in R. It means the vector from Q to P is also fixed in R. Now suppose that it is interested, or it is desired, to determine the velocity of P relative to Q, I should say velocity and acceleration of P relative to Q as viewed by an observer in reference frame A. So let's take that. Let's compute those rates of change and see what we get. So the first thing is as follows: is that the velocity of P relative to Q in A is equal to the rate of change in reference frame A of the position of P relative to Q. But because the position of P relative to Q is fixed in the rigid body, we can write this as, using the transport theorem, as d dt in R of the position of P relative to Q plus the angular velocity of R in A crossed with the position of P relative to Q. But Rp relative to Q is fixed in R, so that implies that the rate of change in R of Rp relative to Q is equal to 0, and that comes from what we had before, that the position of P relative to Q is fixed in R. So that first term is 0, which gives that the velocity of P relative to Q in reference frame A is equal to the angular velocity of the body in reference frame A crossed with the position of P relative to Q, which gives that the velocity of P minus the velocity of Q in reference frame A is equal to the angular velocity of R in A crossed with the position of P minus the position of Q. So that's the first result for the kinematics between 2 points on a rigid body, which gives you the relative velocity between 2 points on a rigid body as viewed by an observer in an arbitrary frame A. So now let's do the next derivative, which is we know that the acceleration of P relative to Q in A is equal to the rate of change in A of the velocity of P relative to Q in A. But that is equal to the rate of change in A of the result that I just computed, which is the angular velocity of R in A crossed with the position of P relative to Q. And that equals, from the product rule of differentiation, the rate of change in A of the angular velocity of R in A crossed with the position of P relative to Q plus the angular velocity of R in A crossed with d dt in A of the position of P relative to Q. Now, we remember or recall that the angular acceleration between R and A is equal to the rate of change in A of the angular velocity of R in A. Now, of course, if we applied the transport theorem to this, this is equal to d dt in R of omega Ra plus omega Ra crossed with omega Ra, but this last term is 0 because the cross product of a vector with itself is 0. So the angular acceleration of r in A, which is the rate of change in A of the angular velocity between the two frames, it's the same thing as taking the rate of change in the rigid body of the angular velocity between the two frames. But we'll just leave this first part here as is. So what we get is that, we just substitute in, that the acceleration of p relative to q in A is equal to, so let's go back over here. Now if we substitute, we get alpha Ra crossed with the position of p relative to q plus omega Ra, and then crossed with, now we get omega Ra, because I'm going to substitute d dt in A of the position of p relative to q, which is omega Ra crossed with the position of p relative to q. From which we can actually write this out in full form, which is the acceleration of p in A minus the acceleration of q in A is equal to alpha Ra crossed with the position of p relative to q plus omega Ra crossed with omega Ra crossed with Rp minus Rq. So that's the second result. Now, the two results that we've gotten, so if we write them out, let's write them out. We get that the velocity of p in A minus the velocity of q in A is equal to omega Ra crossed with the position of p minus the position of q. And we get that the acceleration of p in A minus the acceleration of q in A is equal to alpha Ra crossed with the position of p minus the position of q plus omega Ra crossed with omega Ra crossed with the position of p minus the position of q. Now actually, just to be completely consistent with the notation, we can change this up here. Alpha Ra crossed with the position of p minus the position of q. So now that gives us the relationship between the velocity and acceleration between 2 points on a rigid body. And we can actually use that to be able to solve a problem. So let's actually look at an example and see how this plays out on an example. So in this example, we have two arms. The first arm has a length of L1. The second arm has a length of L2. The angle formed by the horizontal in the first arm is actually theta, and the angle formed from the first arm to the second arm is phi. And we'll call the point where the first arm is hinged, we'll call it O. We'll call the hinge point between the two arms Q, and then we'll call the end of the second arm, we'll call it phi. Now, in order to solve this problem, I can see that there are two rotations. So what are we interested in? So let's look at the objective. The objective is to determine the velocity and acceleration of point P as viewed by an observer fixed to the ground. Now, in order to do this, we're actually going to use the rigid body kinematics results that we developed previously, because these are two rigid bodies, because they're objects with their arms with constant length. So the thing that we have to do, for starters, is we have to look at the fact that there are two rotations in this problem, which means that we're going to need 3 reference frames. Now, these reference frames are going to be as follows, is that the base reference frame is the ground, which I'll denote G. The first rotating frame is the first arm, which we'll denote as A, and the second rotating frame, which also happens to be a translating frame because point Q translates relative to the ground. This is going to be the second arm, and we'll denote that as B. So now let's look at coordinate systems that are fixed in each of these reference frames. So here's the ground, and then A is arm 1, and then B is arm 2. So the ground, its coordinates are going to be as follows. Origin is going to be at O. I'm going to put EX is going to be along OQ when theta equals 0. EZ is going to be out of the page. And then EY is equal to EZ crossed with EX. The second reference frame is the arm as the first arm, and the origin of the coordinate system for the first arm is also going to be at O. I'm going to put little ex along OQ. Little ez is going to equal big EZ, and then little ey is going to equal little ez crossed with little ex. And then the third reference frame, the third coordinate system, which is going to be fixed in the third reference frame, is got to be fixed in the second arm. So the origin of this coordinate system is going to be at Q, because Q is fixed in the second arm. I'm going to put UX along QP. UZ is going to equal little ez, which also happens to equal big EZ. And then UY is going to equal UZ crossed with UX. Now let's look at a picture, and then we'll move from there. So the picture looks like this: is that here is the ground fixed coordinate system. Let's draw them all. Let's see. Here's the ground fixed coordinate system, which has EX, EY, and then EZ. And then the first rotating system, which is fixed in the first arm, is going to have EX, and then little ey, and then little ez. And then the second rotating coordinate system is going to have its axes, or its basis vectors, as ux, uy, and little uz. The angle from the big EX to little ex is going to be theta. The angle from EY to little ey is going to be theta. And then the angle from little ex to ux is going to be phi, which makes the angle from little ey to little uy also phi. Now, once we do that, we want to compute the velocity and acceleration of point P as viewed by an observer fixed to the ground. So we're actually going to do this in two stages. So we're going to do it as follows: is that we know that both arms are rigid bodies. So as a result, we know that for arm 1, O and Q are fixed in A, right? And then for arm 2, we know that Q and P are fixed in B. because A is arm 1 and B is arm 2. So what we can do is we can actually do this calculation to get the velocity and acceleration of point P in two pieces. The first part is we're going to get the velocity of point Q in the ground minus the velocity of point O in the ground. Now, because points Q and O are both fixed in arm A, we know that this can be written as the angular velocity of A in G crossed with RQ minus RO. But we have a few things here. We know that the angular velocity of A in G is equal to theta dot times little ez. We also know that RQ minus RO, because we're measuring all our distances ultimately from O to be able to get rates of change in the ground, this is just going to equal L1 times little ex. So as a result of that, we get that the velocity of point Q in A minus the velocity of point O in A is equal to theta dot Ez crossed with L1 Ex, which is equal to L1 theta dot times Ey. But point O is fixed in, sorry, this should be G. We know that point O is fixed in G. So O is fixed in G. That implies that the velocity of point O in G is equal to 0, from which we get that the velocity of point Q in G is equal to L1 theta dot times Ey. Now, next we can get the acceleration. So the acceleration of point Q in G minus the acceleration of O in G is equal to the angular acceleration of A in G crossed with RQ minus RO plus the angular velocity of A in G crossed with the angular velocity of A in G crossed with RQ minus RO. But again, remember that the angular acceleration of A in G is equal to the rate of change in G of the angular velocity of A in G, which also happens to equal the rate of change in A of the angular velocity of A in G. And if we look at the angular velocity of A in G, it's equal to theta dot Ez. So this is equal to theta double dot Ez, because little ez is fixed in reference frame A. So we now have the angular acceleration. Now we have all the information from which we can compute this relative acceleration. The acceleration of Q in G minus the acceleration of O in G is equal to theta double dot times Ez crossed with the position of Q relative to O. But that's equal to L1 times Ex. And then the second term is going to equal plus theta dot Ez crossed with theta dot Ez crossed with L1 times Ex. So if I simplify this, I get L1 theta double dot Ey, and then if I take these cross products, Ez crossed with Ex is minus Ey, and Ez crossed with the resulting Ey is, so Ez crossed with Ex is Ey, and Ez crossed with Ey is minus Ex. So this gives me minus L1 theta dot squared times Ex. Now, because O is fixed in G, that implies that the acceleration of O in G is 0, from which we get that the acceleration of Q in G is equal to minus L1 theta dot squared Ex plus L1 theta double dot Ey. Now we have all the information about the motion of point Q. We have the velocity of point Q from before. We have the acceleration of point Q from before. So now we don't need to worry about Q at all. Now we're going to look at the relative motion between P and Q. So next, determine the motion of P relative to Q. in reference frame G. So what do we have? So the first thing we have is as follows. We have that the velocity of point velocity of point P in G minus the velocity of point Q in G is equal to the angular velocity of B in G crossed with the position of P minus the position of Q. Now, why did we do that? We did that because, remember, points P and Q are both fixed in B, and we want the rate of change in reference frame G, so we're going to be applying this equation that relates the velocity between 2 points in a rigid body to get the rate of change in G between these velocities in terms of, or transporting from B to G. This is essentially the transport theorem for a rigid body. Now, the angular velocity of B in G is equal to the angular velocity of A in G plus the angular velocity of B in A. We already have the angular velocity of A in G. We need the angular velocity of B in A. The angular velocity of B in A is equal to phi dot times uz. So this gives that the angular velocity of B in G is equal to theta dot times ez plus phi dot times uz. But since ez is equal to uz, we get theta dot plus phi dot times uz. Now, we can actually use that information to compute the velocity of point P relative to Q and G. We know that the position of P minus the position of Q, which also happens to be the position of P relative to Q, is equal to L2 times Ux, because we've defined Ux to be along one of its directions to be along the second arm, which is along the arm, the reference frame B. So this gives us that the velocity of point P in G minus the velocity of Q in G is equal to theta dot plus phi dot times uz crossed with L2 times Ux, which gives L2 times theta dot plus phi dot times uy. So the velocity of point P in G minus the velocity of point Q in G is equal to L2 times theta dot plus phi dot times uy. Now, we already have the velocity of point Q from before. The velocity of point Q is equal to L1 theta dot ey. So this tells me that the velocity of point P in G is equal to L1 theta dot times ey plus L2 times theta dot plus phi dot times u sub y. So now we're done with the velocity of point P. We can now move on to computing the acceleration. So we know that the acceleration of point P in G minus the acceleration of Q in G is equal to the angular acceleration of B in G crossed with the position of P minus the position of Q plus the angular velocity of B in G crossed with the angular velocity of B in G crossed with RP minus RQ. Now, let's go through and compute the angular acceleration because we need it. The angular acceleration of B in G is equal to the rate of change in reference frame G of the angular velocity of B in G, which is also equal to the rate of change in B of the angular velocity of B in G. But the angular velocity of B in G, as we had from before, is theta dot plus phi dot times uz, and uz is fixed in reference frame B. So this gives me theta double dot plus phi double dot times uz. So then we get the following result. The acceleration of P in G minus the acceleration of Q in G is equal to theta double dot plus phi double dot times uz crossed with L2 times, L2 times Ux, because that's the position of P minus the position of Q, plus theta dot plus phi dot times uz crossed with theta dot plus phi dot times uz crossed with L2 times U x, which is equal to, now u z crossed with ux is uy, so we get L2 times theta double dot plus phi double dot times uy, and then uz crossed with ux is uy, and uz crossed with ui is minus ux, so we get minus L2 times theta dot plus phi dot squared times u x, which gives minus L2 times theta dot plus phi dot squared times ux plus L2 times theta double dot plus phi double dot times uy. Now what we can do is we can substitute the acceleration of point Q and G from what we computed before. Remember that we computed the acceleration of point Q already, so therefore the acceleration of point P in G, which is equal to the acceleration of Q in G, if I take it to the other side, I get minus L1 theta dot squared times EX plus L1 times theta double dot times EY minus L2 times theta dot plus phi dot squared times UX plus L2 times theta double dot plus phi double dot times U sub y. You'll notice that those two parts of the acceleration are expressed in two different bases. But what did I do in order to solve this problem? What's important is that the first thing I did was I looked at points O and Q, and I saw that they were fixed in the first rigid body. So this was the procedure, is that points O and Q are fixed in the first arm, which I called A. So therefore, we applied the relative velocity and acceleration results to points O and Q using reference frame A. And then what we did was we looked at the points Q and P. So first thing here is to write these results down. We said the velocity of Q in G minus the velocity of O in G is equal to the angular velocity of A in G crossed with RQ minus RO. And that's what I mean by we used reference frame A. We went from A to G. And then the acceleration of Q in G minus the acceleration of O in G was equal to alpha AG crossed with RQ minus RO plus the angular velocity of A in G crossed with the angular velocity of A in G crossed with RQ minus RO. Now, that takes care of that part of the computation. The second part was, so this is part one. Part two was that points Q and P are fixed in the second arm, which I called B. So this part, we applied the relative velocity and acceleration results to points Q and P using reference frame B. And what do I mean by that? that means that the velocity of point P in G minus the velocity of point Q in G was equal to the angular velocity of B in G crossed with RP minus RQ, and the acceleration of P in G minus the acceleration of Q in G is equal to the angular acceleration of B in G crossed with RP minus RQ plus the angular velocity of B in G crossed with the angular velocity of B in G crossed with RP minus RQ. So we actually used the results again. Here you notice that we used points O and Q fixed in A, and here we used points Q and P fixed in B. That's how we did it. So this example shows you how you can use the rigid body, the relationship between the velocity and acceleration between 2 points on a rigid body to compute the accelerations in cases where you know that the points maintain a constant distance from one another because they're fixed in the same rigid body. So now what we're going to do is we're going to move on to another topic which comes up a lot in rigid body kinematics, and that's what's called the kinematics of rolling and sliding. Now, the way this works is as follows. And we're going to deal with a body that's in contact or in continuous contact with another body. So consider a rigid body, R, moving while in continuous contact with another rigid body, which I'll denote S. So here's what the picture looks like. We have this second rigid body, we'll call it S, so we'll start with S. Here's S. And then moving while in continuous contact with S is another rigid body, which I'll denote as R. Let's draw this a little better. Okay, so here's R. And there's a point that is the point which I'm going to call the point of contact. So I'm going to call C the point of contact. So C is the point of contact between R and S. Now what's really important about this is that this is also what's called the instantaneous point of contact. Now what I mean by the instantaneous point of contact is that the point of contact may actually change as time evolves. In other words, the point on R, which is in contact with S at one instant of time, may not be the same point on R that's in contact with even the same point on S at a different point in time. As time evolves, that point of contact is going to change. Now, the way that we describe this is as follows. So we have C, which is the point of contact. We're going to define two quantities, okay? And we have to be really careful about the notation that we use here. Is that at any instant of time, the velocity of point C on R may be different from the velocity of point C on S as viewed by an observer in an arbitrary reference frame A. So in other words, if I'm an observer in some arbitrary frame, let's call this arbitrary frame A. Here's my frame A out here. And I'm looking at the motion of point C, but I'm looking at that motion as it pertains to how point C being on rigid body R, that motion may be different from the motion of point C on rigid body S, because point C is a point that's common to both of them, but it's also a point on each body separately. So we're going to actually define two quantities that will allow us to distinguish between these two. The first one is the velocity of point C on rigid body R in reference frame A is equal to the velocity of C on rigid body R as viewed by an observer in reference frame A. The second one is the velocity of point C on S in A is equal to the velocity of C on rigid body S as viewed by an observer in reference frame A. Now, we're going to define two different types of contact. The first is what's called rolling, and the second is what's called sliding. So we say, so body R is said to roll on body S if the following condition is met: that the velocity of point C on R in A is equal to the velocity of point C on S in A. This is what's called the rolling condition. We define rolling to be when the velocity of the point of contact on both bodies is the same when taken in any arbitrary reference frame A. If VCR in A is not equal to VCS in A, then body R is said to slide on body S. So in other words, what we mean is that VCRA, if it's not equal to VCSA, then this is what's called the sliding condition. Now, what it really means is that sliding is equal to not rolling. So the only thing we can say about sliding is that if it's not rolling, we say that it's sliding. Because remember, we said that body R is moving while in continuous contact with body S. So as a result of that, we we only define rolling to be that condition where the instantaneous point of contact, the velocity on either body is the same, and we define anything else as sliding. Now, in order to see how this works, let's take an example. And this example actually sort of identifies how this works. Is that in this example, what we're going to do is we're going to consider the motion of a circular disk, or equivalently a circular cylinder, rolling on a flat surface. Okay, now I'm going to label the point of contact here as C. I'm going to call the center of the disk, I'm going to call it O. And what we're going to do is we're going to look at the velocity and acceleration of point C as viewed by an observer fixed to the ground. Now, in order to do that, I'm going to define the following quantity. I'm going to define the angle that the disk rolls. I'm going to define it as the angle theta. So what we're going to do is we're going to put a point P out here. P is actually going to be fixed to the disk, and the angle theta that's formed with the vertically upward direction is as shown in the figure. So O is the center of the disk, C is the instantaneous point of contact, and P is some point that is fixed to the disk. So in order to solve this problem, we actually need two reference frames because there's one rotation. So let's write down the objective. The objective, actually there are a couple of objectives. So the objectives are to determine the velocity and acceleration of points O and C as viewed by an observer fixed to the ground. Now, the important part of this problem is we have to use a condition for rolling. So what we're going to do is we're going to say that point C, or we're going to say that the disk rolls without slip which is the same thing as saying rolling, on the ground. So when we say rolling, we actually say it's no slip. That's another way of saying rolling, is saying no slip. So we're actually going to impose the rolling condition in the process of solving this problem. So let's look at the setup here. We have one rotation. That's due to the disk, which implies we need two reference frames. Those two reference frames are the base reference frame, which is the ground, and I'll denote that D, and the first rotating reference frame, which is also a translating reference frame because point O is translating, and that's the disk, which I'm going to denote as D. Now, here's what we're going to do. We have to set up coordinates fixed to each one of these frames. So G is going to equal the ground. And we're going to fix a coordinate system as follows. We're going to put the origin at O when t equals 0. So wherever O is when t equals 0, that's the origin. I'm going to put EX, I'm going to say to the right. And then EZ is going to be into the page. And then EY is is going to equal EZ crossed with EX. The reason I put EZ into the page is because of the rotation of the disk. D is going to equal the disk. I'm going to put the origin of the coordinate system fixed to the disk at O. I'm going to put the first basis vector fixed to the disk. I'm going to call it ER, is going to be along OP. I'm going to put EZ into the page, so it's going to be the same direction as big EZ, and then E theta is going to equal EZ crossed with ER. Now, let's look at how we have to do this problem. This problem, it takes a little bit of work to figure out how to do this problem because we have to use relative position and relative velocity. So the first thing is to notice that we need to figure out the velocity and acceleration of point O. But we also have to take into account the fact that this disk rolls without slip. So the first thing I'm going to do is I'm going to write that condition down. Is the disk rolls without slip on the ground. So given the fact that it rolls without slip on the ground, that means the velocity of point C on the disk as viewed by an observer fixed to the ground has to equal the velocity of point C on the ground as viewed by an observer fixed to the ground. But the velocity of point C on the ground as viewed by an observer fixed to the ground is 0, because the ground doesn't move relative to the ground, so that's equal to 0, which tells me that the velocity of point C on the disk as viewed by an observer fixed to the ground is 0. But notice that, so let's write this down, but observe that C is a point that instantaneously is fixed to the ground and to the disk. That means that point C is a point on the disk, which means that we can actually use the fact that point O is fixed to the disk, and we can use that fact to be able to relate the velocity of point O to the velocity of point C, because they're both fixed to the disk. Now, this may be hard to see at first, but points O and C are both points on the disk. So I can apply the relative velocity between 2 points on a rigid body in order to get the difference between the velocities of points O and point C. So this is equal to the angular velocity of the disk as viewed by an observer fixed to the ground crossed with RO minus RC. But we already know that the velocity of point C is 0 because we got that from the no-slip condition from before, right? So velocity of point C on the ground is the velocity of point C on the disk in the ground because I'm using point C and point O as points that are on the disk. So now let's use this information to be able to figure out the rest, which is that I know that the angular velocity of the disk as viewed by an observer fixed to the ground is equal to theta dot times EZ. Just from the fact that the disk is rotating, the angle theta from the vertically upward direction is where the vertically upward direction is fixed to the ground. That angle theta measures the rotation of the disk, so the angular velocity is theta dot EZ. The next thing I need is I need the position of O minus the position of C. Well, let's just assume that the disk has a radius of R. Okay, so the radius of the disk is capital R. Well, if I look at where O is relative to C, I can see the following thing. Look at how I defined my coordinate system. I defined EX to the right, I defined EZ into the page, and EY is equal to EZ crossed with EX. So let's look at a little picture here. EX is this direction, EZ is into the page, and then EZ crossed with EX puts EY downward. So this tells me that the position of O minus the position of C is equal to minus R times EY. It's a distance R in the negative EY directions. O is from C. So therefore, the velocity of point O in G minus the velocity of point C in G is equal to theta dot EZ crossed with minus R EY, which is equal to R theta dot times EX, because little ez is the same thing as big EZ. So the velocity of point O in G minus the velocity of point C in G is that. But I already know that the velocity of point C in G is 0. This is from the no-slip condition, or the rolling condition, right? So therefore, the velocity of point O in G is equal to R theta dot times EX. And from that, we can actually very quickly get the acceleration of point O. So we know that the acceleration of point O is just equal to the rate of change in G of the velocity of point O, but because EX is fixed to the ground, this just becomes R theta double dot times EX, because there's no transport that's needed because the basis vector EX is already fixed to the ground. So as a result of that, I don't need to apply any transport. So now we have the velocity and acceleration of point O. Now let's get the velocity and acceleration of point C. Well, we already have the velocity of point C. We already know that the velocity of point C is 0, and again, that's from the rolling condition. Now we need the acceleration of point O. We want the acceleration of point O as viewed by an observer fixed to the ground. So how do we get that? Well, we know that C and O are points on the disk. So that means that the acceleration of point O minus the acceleration of point C is equal to, let's do it the other way around. The acceleration of point C minus the acceleration of point O is equal to the angular acceleration of the disk as viewed by an observer fixed to the ground crossed with RC minus RO plus the angular velocity of the disk in the ground crossed with the angular velocity of the disk in the ground crossed with RC minus RO. Now, let's look at this. We already have the acceleration of point O. I just computed it. It's on the previous page. So now I need the rest of this. The angular velocity of the disk in the ground is equal to the rate of change in the ground of the angular velocity of the disk in the ground, which is also equal to the rate of change in the disk of the angular velocity of the disk in the ground. And that's equal to theta double dot times EZ. Now, again, RC minus RO is equal to minus RO minus RC, but RO minus RC was equal to minus REY, so this is equal to R times EY. Now, if we substitute everything in, what do we get? We get the acceleration of point C in G minus the acceleration of O in G is equal to theta double dot EZ crossed with REY, and then we get plus theta dot EZ crossed with theta dot EZ, and actually, just to be completely consistent with our notation, we use little ez, and then crossed with R EY. And we should do the same thing here. We should use little ez. So now let's compute this. The acceleration of point C in G minus the acceleration of O in G is equal to, well, let's look. we've got EZ crossed with EY, which is minus EX. So we get minus R theta double dot times EX. That's the first term. The second term here is EZ crossed with EY is minus EX, and then EZ crossed with EX is equal to EY. So this gives us minus R times theta dot squared times E sub what? Well, EZ crossed with EX is EZ crossed with EY is EX, EZ crossed with EX is EY, so this gives me an EY. Now, if you want to see that step perhaps in a little bit more detail, we can put this in the following aside here, and we can show it just to make it clear. We've got theta dot EZ crossed with theta dot EZ crossed with REY, which is equal to theta dot EZ crossed with EY is minus EX. I got minus R theta dot times EX. And then this is equal to minus R theta dot squared. EZ crossed with EX is EY. So that's how I got that result. Now, from here, we actually can use this last result, and we get the acceleration of C in G minus the acceleration of O in G is equal to minus R theta double dot EX and then minus R theta dot squared times EY. But the acceleration of O, I already got it. It's R theta double dot EX. So this gives me acceleration of C in G minus R theta double dot EX is equal to minus R theta double dot EX minus R theta dot squared times EY. And this gives me that the acceleration of C in G is equal to minus R theta dot squared times EY. You'll notice something. This is not equal to 0. So even though the disk is rolling without slip, let's go back to the original picture. The disk is rolling without slip on the ground, and the velocity of the point of contact is equal to 0 because the velocity of the point of contact on the disk is the same as the velocity of the point of contact on the ground, and we're measuring everything relative to the ground. And that's equal, so that means the velocity of point of contact on the disk is 0. Just because the velocity of the point of contact on the disk is 0 does not mean that the acceleration of the point of contact is 0. So let's write that down. Just because the velocity of point C on the disk in the ground is equal to 0 does not mean that the acceleration of the point of contact on the disk is equal to 0. In this case, let's write this down on the next page. In this case, the instantaneous point of contact has 0 velocity relative to the ground, but has non-zero velocity relative to the ground. Non-zero acceleration relative to G. Relative to G. And what direction is that acceleration? So if I draw the picture of the disk again, here's the disk, and here's the ground, and then here's this point C. It turns out that the acceleration of point C as viewed by an observer fixed to the ground is in that direction. Because remember, my coordinate system was set up so that I had EX this way, I had EZ into the page, and then I had EY that way. So as a result, I actually can see that the acceleration points in the negative EY direction. So if I go back to the original picture, the acceleration actually points in the direction from C to point O, because point O was up here. So it actually points in that direction. It points towards the center of the disk. So that's the second example that I wanted, or the second example I wanted to do. The first example was showing the relationship between 2 points on a rigid body and how we can compute velocity and acceleration. The second part describes rolling and sliding. Now, there's one last thing that may be worth pointing out here, is that if it turns out that the disk actually slides on the ground, then we couldn't have used the rolling condition, because the rolling condition is only applicable when the disk rolls on the ground. It actually takes out a degree of freedom. But the disk sliding doesn't take out that degree of freedom, in which case we would actually have had to, we wouldn't have been able to do this with one variable. We would have had to actually use two variables. We would have had to use both both a horizontal coordinate and an angle. And that's a different problem, because now the disk actually moves with slip on the ground, in which case there's an extra degree of freedom which doesn't exist when the disk rolls without slip or rolls on the ground. So that's the end of this lecture. In the next lecture, we're going to talk about more kinematics of rigid bodies, and we're going to talk about orientations of a rigid body.